Hello friends. In this series we will discuss fundamentals of electric machines, and we will go from fundamentals to advanced topics in electric machines like vector control, direct torque control, etc. And this is the first lecture on this series, and today we will discuss the basic concepts required in the electric machines. So we'll cover basically the four things: Ampere's law, transformer action, generator action, and motor action. So let me give you just few statements. Any current carrying conductor produces a magnetic field. Any current carrying conductor produces a magnetic field. That is Ampere's law. Okay. Any current carrying conductor produces a magnetic field. So now we got the magnetic field. Okay. We pass some current, there is a magnetic field. Okay. If there is a change in magnetic field and you put a coil in that changing magnetic field, then and a voltage will be induced. Okay, that is called transformer action. Okay, then there is a conductor. So in transformer action, what was the thing? Conductor was stationary, magnetic field was changing with respect to time. Okay, so there is a change in magnetic field, but the conductor is placed in that changing magnetic field. So there is an EMF induced. Generator action, magnetic field is stationary, conductor is moving in that conductor is moving in that stationary magnetic field. Okay, so then an EMF is induced. Okay, that is called generator action. Motor action, if there is a current carrying conductor placed in a magnetic field, there will be a force on it. Okay, so that is the motor action. If there is a current carrying conductor in a magnetic field, a force will be applied by the magnetic field on that conductor. Okay, we will derive all the principles of electric machines starting from these basic statements. So we go to Ampere's law. Okay, any current carrying conductor produces a magnetic field. So this establishes a relationship between current and the produced magnetic field. Okay,
Current carrying conductor produces a magnetic field. Let us say we have a current carrying conductor and I take the cross section of this conductor at this point and I look it from this side. Then I have to draw in this cross section of the conductor a symbol like this, which means the current is going into the screen away from me, and we denote it like cross. Now let us say I look at it from this side. Then the current is flowing towards me, so I represent it with the dot. In general, for any quantity, dot means the direction of the quantity is away from the screen towards me, and cross means the direction is towards the screen. Now let us see the direction of magnetic field that is produced by the current. It is determined by the right hand screw rule, which is shown by this. If the thumb points to the direction of the current, the finger points the direction of the magnetic field. If we have cross section of the conductor with cross, the direction of magnetic field will be like this, which is clockwise. And if we have cross section of the conductor with dot as the direction of current, the direction of magnetic field will be like this, anti-clockwise. Now let us consider the magnetic core here. And we have a wire wound around this magnetic core like this, as shown in this figure. Let us find the direction of the magnetic field. So let us consider the cross section of the core. We'll discuss more in detail about the core in the latter part of the lecture. The cross section of the core is taken through this plane. So it will be like this. And then we have conductors like this. What will be the direction of current in the conductors in this side? We will have cross. What will be the direction of the current on the conductors at this side? It will be dot. Now let us look at the first turn. That is these. What will be the direction of the magnetic field? So let us say it's here, dot and cross. So because of cross, there is a clockwise magnetic field, and because of dot, there is anti-clockwise. Now let us look at the second turn. Again, the magnetic field, because of cross, will be clockwise, and because of dot, it will be anti-clockwise. Now let us focus at this part. The direction of the magnetic field shown by red is opposite to the direction of the magnetic field shown by green. Same here. So the net magnetic field in this region will be cancelled. So if we take the resultant magnetic field because of these two turns, then the magnetic field will be like this. We can extend this analysis, and then we can say the resultant magnetic field will have the direction like this. Now we can say if the direction of current is given by our fingers, then the magnetic field is in the direction of thumb. After knowing the direction, let us find how to measure the field. We said magnetic field several times, but what is the measure of it? It is given by this equation, where H is the magnetic field intensity. So H is nothing but magnetic field intensity. And I net is the net current. This equation shows that the integral of magnetic field intensity over a closed loop is equal to the net current enclosed by the loop. Now if we consider this closed path given by this dotted line, then the magnetic field integral is given by H times L. L is the length of this path. So the integral is H times L, and this is equal to the net current enclosed by this loop, and the net current enclosed by this loop is number of turns. So in this case, in this example, we have 3 turns, 1, 2 and 3. So it is 3 times I. So n equal to 3 in this case. But in general, we can say it is n times I. So what is the magnetic field intensity? Magnetic field intensity is number of turns multiplied by current divided by the length of the path.